Now for the moment, I am recording the screen using my own laptop, but I'm not using the screen recording from the WebEx. So you see that in the WebEx you don't see the lecture is being recorded, but actually it's being recorded on my screen. Okay. Right. So we are going to talk about the part 8 from the lecture notes. You can tag on this thing. Let me go back to my home. Okay, so we are on this so we are somewhere in the middle of part 8. So you click on this, you'll be brought to the web page. Then you can look at the lecture notes, or you can download the lecture notes. Okay, but again, the lecture note cannot be viewed unless if you go to the Google Colab or you download this. Okay, fine. So I'm going to use my own versions of my lecture notes. So we are on part 8, first order differential equations. Okay, so so my screen is here. Let me drag my screen a little bit. Okay, so you can see me. Okay, so this is my screen. Now we are going to talk about how to do the numerical integrations for the first order differential equations. Now again, first order differential equations like this one on the example on the screens. If you integrate it once, then it will give you the solution. Okay, so this is only happening in first order differential equations. If you're talking about second order differential equations, then things will become more complicated. So you integrate once, second order differential equation may not get you the solutions. Okay, you're going to give you the first order differential equations if you integrate the second order differential equation once. But anyway, we are going to do an exercise on how to solve this differential equation. Now we have actually solved this already in the previous case. For example, if you have this very simple differential equation, how do you solve it? Right? So let me just to remind you again, in case you have forgotten, last week we have talked about how to perform a differential equations for this exercise where we are solving the differential equations, first order differential equations for the Beer-Lambert law. Okay, so I think last week there was a slight mistake on this. So di dz is equal to minus alpha I. So I think last week it was like delta alpha z. So just be aware that some corrections has been made. Okay, so today we are going to demonstrate some examples. So I think in Python code, it is very important to do a lot of practices. So you would have to do many times the integrations exercises, or you will forget. Okay, so this is a very generic situation where you have a first order differential equation, solve it for me. So you can run this, but let us go through this one by one. I'll take maybe a few minutes to go through this one by one. See, my purpose is to show you the details of how to perform the integrations of the first order differential equation to get the answer. So demonstrations of these code step by step will help you hopefully to get you understand better how to do it. Now later on we are going to deal with much more complicated differential equations. For example, we're going to deal with couple first order differential equations, couple second order differential equation, and things like that. Okay, so if you cannot solve the first order differential equations, then it will be difficult for you. Okay, so let us begin. Let us try to solve this. dy dt equals to minus y plus 1, and for first order differential equations, you must provide an initial conditions. So there's only one initial condition that you have to provide. So let us revise how we do this using NumPy. So in this case, we need what? We need sciencepy, right? So we have to import sciencepy dot integrate. So we are going to use from Science Pi integrate, I think. From Science Pi integrate import. So the package we're going to use for this is the ODE INT. Right? So this is ordinary differential equation, ODE INT. So this is what we need. And since we're going to plot, we always need matplotlib dot pyplot as import matplotlib as PLT. So these are usually what we need, and usually we also need import numpy as MP. Okay, so these are the default that we need. So to solve this differential equation, again, you need to define a model function in which the model function would be used to generate the expressions of the differential equation dy dt. So you need a model function that will return the expression of dy dt. So in this case, the expression for dy dt is just minus y plus 1. Okay. So here, again, as I explained last week, y is the dependent variable, which is a function we are looking for. And then t that I try to highlight here, is the independent variables. There's only one dependent variable and one independent variable. So things are quite simple here. So let us define the model. So you define a model functions that would emit the y as your dependent variables, and then your independent variable would be t. Okay, so I think this is what I remember. Now I don't really refer to the code downstairs, so I'm actually showing you the steps all from my own brain. Okay, so I might make some mistakes because I'm not really familiar with the syntax, but as long as you practice a lot of times, and then you will be able to remember the syntax. So the syntax for the function is to read in the independent variable. You have to define an independent variable, which is y, an independent variable, which is t. So this y is the function we are looking for. So you want the model to return an expression for dy dt. Okay, so you have to define what is your dy dt. So dy dt is an expression which is equals to minus y plus 1. I think that is what you need for defining the model. So model, at the end of the model, you will return the expression of dy dt. Then what you do is, in order to solve this, you just have to use the ODE INT. And in ODE INT, you have to, of course, tell the solver. So ODE INT is what they call the first order is a differential equation solver. So you call the differential equation solver, and then you tell the differential equation solver what is your function to solve. So the function to solve is embedded in the model. Then what is the next thing you have to put in? So wait, let me run this once. So if you can't remember, the integrate has an error here. So the syntax for using model, the ODE INT, if you can't remember it, you just always type ODE INT. Right? So if you look at this, again, you need to provide the functions, so which is a model, and then you have to provide the initial conditions. So then you have to provide the independent variables. So the second entry that goes into the ODE INT is the initial condition. So I call this initial conditions. Okay, so init condition. I think it's okay. So the initial condition is what? The initial condition is the values of y when t is 0 and is equals to 0. So to do this, what I do is I say, okay, y naught is a number which is 0, and then initial condition is just equals to y naught. Okay, but this is not going to work, because if you look at the requirement for y naught, so it says here the y naught is an array, like it has to be in an array. But here I'm defining y as not an array but a number. So most probably I will have to put this into a bracket. But let me not to put in a bracket and see whether it works. It should not work. Okay, but if it works, then we just take it as a number. But I think this has to be included in the form of a matrix. Then you have to call your independent variable t. But what is t? T should be the linear space for which you want to find the solution for y, right? So y is a function of t. So what is the t value? Then you have to define your t. So you have to define your t. And since this t is a range, so we will put this into ARR. So when I see an ARR, that means this quantity t ARR should refers to a list. Okay. So I have not really explained in detail last time the difference between a list, an array, and a tuple, but they are more or less the same, but slightly different. Okay. But anyway, if the list doesn't work, then somehow you have to sometime translate the list into an array. Okay. So the array is a number which I would generate using linspace. So you have to decide where is your number starting from. So you will have to plot this for y beginning from t at 0. So the first number in your linspace of t must be 0, and then it will end somewhere, maybe say 10. Okay. So then you need say 100 points between them. So this is the linear space for the independent variable. Then this would be your t array. So by doing that, when you press a button, this ODE would call the model, and then what you do is that when you call the model, it would put this initial condition, the values of initial condition, into the model. So since this initial conditions has only one number, so it means that the independent variable has only one component, and it would assign y equals to 0 into the values of y into the model. So when the model is called, the values of 0 will be first passed into the definition of dy dt, so that dy dt would be 1, and then it will return 1. After that, this 1 will be put in to model again. So in the second round, the y value would be changed. But anyway, we don't really talk about the details of how this thing is done. But what I'm trying to say is that when the ODE model, ODE INT is called, the Python actually go through a looping process, right? So you would put in y0, then it will get y1, and then from y1 you get y2, and then from y2 you get y3. So there is a looping process that is happening when this ODE is called. But in order to begin the looping process to have the solution for y, the loop has to begin with some known value. So this is the purpose of the initial conditions. So let's press the button. Okay, so I have error. So it's always an error. So any condition is not defined. I think this one, any condition COND, right? It's not COD, CON, right? So it's defined. So now you see that this is the output that is an ODE. So be very careful about this. This ODE is actually an array, a column vector. An array, so maybe I just call this SOL, okay? So let us try to print out the shape of SOL. So it is a column, that means it is 100 times 1 in shape. So you can print out the shape of this shape. So if you say shape np.shape, you use the numpy, it has a function called np shape, then it will tell you that this is actually an array, not an array, actually it's an column vector, where the column has 100 row and has one column. Okay, so what I'm trying to tell you is that the solution that is given by the ODE is a column vector. It's not a row vector. Now in other cases, I think in the previous functions, I think what we have learned some package before that, like from SciPy integrate, when you use a quadratic function, QUAD, fit parameter. So the output is not in a column, but the output is in an array. It's in the row vector, but this output is a column vector. So be careful about this. So so the solution is just what you want. Now, what is this solution? This solution refers to the values of y we are looking for. So the output gives you a y value. So now we know what is your t, what is y. Then can we plot the functions? Not quite. So if you say let us plot pl t dot plot So you're going to plot TARR and you plot solution. Well, then you're not going to work because the solution has a shape which is different than the TARR. So maybe I should show you what I meant by that. So if you ask the shape, right, the shape of TARR, so the shape of TARR, shape, anything of shape TARR is a tuple. Well, a tuple in this sense is just a list which is a row of list. It has one row but has 100 columns. I think that no, this is not. This is what you mean by that. Okay, then maybe I'm not quite sure. So maybe let me print out SOL. So in order to plot the ARR, TARR, and SOL, we have to make sure that both the shape and SOL has the same shape, or else it would not work. Okay, so maybe it could, maybe it could not. Maybe okay, let's try it anyway. So let me try to plot this and see what we get. Yes, you get it. So in this case, it works. So let's plot it out. Okay, so there's no complication here. The solution, although it's in a column vector, it can combine with the TARR because both have the same shape. Then this is a solution, right? So this is just what this is doing, right? Then you got the solution that looks exactly like this one. So here I'm using 50 points, but here I'm using 100 points. So you see that the points are closer. So at this moment, then you will be able to solve this differential equation, first order differential, quite easily, right? So you can plot this and then you can calculate this. Okay. Now let us look at another more complicated situations where you have to solve these differential equations. So in order to solve this differential, it's actually not that difficult because this duty is a function of t. So let's see how you do this. So let's just do it again. So as usual, we always need these three things. So let me clear my memory. I restart the kernel. Okay, let's try to plot this again. So again, I need, maybe I just copy and paste this again. Define my function and TARR. Okay, so to solve these equations, I would define my model and then have to decide my linear space. So the linear space has to include 0 and then has to be larger than 10, or else you will not see the overall behaviors of y, right? Okay, so let me maybe not up to 20, 100, just up to 20. So but the space for t is from 0 to 20. Now remember, you have to start from 0 because you need to put in the initial conditions of y at t0. So if you start your t not from 0, then you will not be able to assign the initial condition correctly. Okay, so let us try to define this. What should your model be? So your model would be to return dy dt. So if you rearrange this a little bit, so this equation become dy dt equals to minus y over 5 plus ut over 5. Okay, so that should be the. So you can't really define dy dt, but you can only define dy dt on the left. So this is equals to minus y over 5, okay, and then plus ut. Now what is ut? Now ut is not defined, so we need another function to define ut. Okay, so just define the function u, and this is just normal function. It admits this, and then what you have for ut is a value of, now this has to be a bit tricky because ut is an if function, so you have to assign the values to u based on the values of t. So you have to write an if statement here. So you say if t is less than 10, what happened? Then okay, so then we say ut is equals to 0. Else if, okay, I think it's like this. Else if t is larger or equals to 10, then ut will take on the values of 2. Okay, so that is how you define the GF, but I'm not sure whether this is working correctly. So what I'm going to do is that let me try it out. So I'm going to print out the values of u at, say, 0. Do I get a number? So if I get a number, that means the function for ut is correct. No, it doesn't work. I think the else is like this. Else is not quite true. Else. Okay. So there is a syntax for if and else. Else if, yeah, no, yes, no, I think no, I think else if t is larger than this one. So let me try again. So it seems like this else is a statement that is not correct. So I have forgotten, I'm sorry, that what the else should looks like. But I think it doesn't matter. Maybe you can check the else later. So let me define these things later on. So let me paste the model here. Okay, so I'm still in the process of defining the u. So this is say like this. If t is less than 10, then u is defined as t. So then now I should put an else, but since I do not know how to use an else for the moment, so I say if t is larger than equals to or larger than 10, I think it's a t, yeah, t is equals or larger than 10, then ut would be then equals to 2. I think this would work. So again, the if statement is not correct. If define ut, if ut equals to this, then again if t is larger than 10, then ut equals to 2, then return ut. Okay, so it's correct. So print ut, name t is not defined. Sorry, this should be ut. Okay, u at t equals to 0. Yeah, so I got this. So when I print ut for t equals to say 11, I should get 2. Right, so that is correct. So this is how you define the t. So the better way is to replace this by else, but you can check it out what the else, how to write the else function is. Okay, so let me cut it. So this is how I define the y function. So now the u function has been properly defined. Now, so this u could be easily called by dy dt. Okay, so now we are almost there. So just to check again that things are doing correctly, I would like to print out the values of the model to see whether it works. So let me say y is say equals to 1 and t equals to 0. I should get a number from, so I got a number from the model. So that means the defined model is working, at least it doesn't give me an error. So now I have finished defining my model and my linear space. Then I would have to have the initial conditions. So initial condition, as I shown just now, the initial condition is the values of y0. And what is y0? Y0 is defined to be y0 is defined to be 1. Okay. Then I am now ready to call the ODE int, and then this is my model, and I'm going to supply the init condition. Then I'm going to type in my ARR. So I got this array. So I call this solution for y. So y solution is this. So I'm going to plot and see whether it works. Plot TARR and y solve. So I got an error. Plot is not defined because I forgot to type in this one. So now I got this plot which looks as what I want. Now why do I know that? Because there is a king, right? So obviously this king corresponds to the values when t is happening at 10. So let us overlap on the plot a functions. So let us plot a functions of u versus TARR on u TARR. So how am I going to plot the u function? I'm going to plot on this solution. This is y versus t. I want to plot on top of this and u. So u as a function of t. So how am I going to print these functions and plot it? So this is how I do it. So now this is not going to work. TARR. If you do like this, then this plot will not give you a plot for y, it will give you an error. The reason is because what goes into U has to be a number, but cannot be an array. So you have to print this as an array, then you have to generate a whole array for the values of UT for T in TARR. I think that is how you do it. So this would give you an array for U where the T is lying in TARR. So I still don't get anything. TU for T, something is wrong. For T in TARR. Okay, so let me check this out. So open another one, and I want to see that this should generate an array for me. Yes, it will generate an array for me. So that should be allowing me to plot these functions. So I should be able to plot this. So why I can't plot this? Yeah, okay, I think this is the problem. So I should be a plot. So these two plots will be also, if you do not say anything, you ask the Python to plot one graph and then to plot another graph. So these two by default will be merged together. Right? So they should put in together, and you see that at 10 equals to t equals to 0, there is a king. So this is a solution for these differential equations. So you just have to define the functions through a function of a function. So in your plot, you have to define what is a u and what is a model. Then you will call the function u from the model. This is how you program it. Then you put it up, and then this is the expected result. So this is another example where we solve the differential equation for this one. Okay, so this is just an exercise, a very simple exercise, but now we're going to go into something which is more complicated. So this one is more complicated. Maybe I should not use this as a template because I'm going to change this accidentally. So maybe I should not use this. So maybe I should use another file. Okay, I should use a part 8 file. Not this one. Part 8 first order. Maybe I should use something else. Okay, so this is part 8. I should use this to show you as exercise. I should not use this. Okay, so I'm going to close this so that you don't save. Is this saved already? Never mind, just close it without saving. Okay. So let us go to the next example. The next example is this one. Okay, so we have two differential equations to solve it together. Now you can do this quite easily. Now these are the two. This example where you have a function of x in terms of t and function of y in terms of t. So these are not really a simultaneous equation because the x and y are not really coupled. Okay, well, but what I mean not coupled means that x does not depend on y does not depend on t. This is just a parametric equation. Okay. So a parametric equation basically the variable x and y are not dependent on each other. So t is an independent variable. When t change, then x change according to this equation. When t change, y will change according to this equation. But you cannot say y depend on x or x depend on y. No, it's not true. So this is a very simple equation. So what I'm going to do with this is that I'm going to show you how this set of two differential equations can be solved in one model instead of separating in two models. So again, do this. Okay, maybe I look at this one. So in this example, I define one model for x. So I define the model x, where I define the x dt to be this. And then I define model y, and then I define dy dx equals to 3 minus y. So that is how this equation, number 1, is defined by model X, then this equation is defined by model Y. Then what I do is that to obtain the X solution, I call ODE and model X, then I plot this. And then to obtain the solution for Y, I call the model Y, and then I obtain it. So it's very simple and straightforward. Now let's just try something more slightly different than what you see. Okay, so let me try to cut and paste this one, and then I'll do it again. So I'm going to demonstrate to you, I'm trying to use one single model to solve two equations in one shot. So instead of define two models, you define only one model. So let me just call this model, and then it will read in dependent variable, and then so in this case, I will call the first X as the dependent variable number. So this dependent variable, I'm going to use it as an a list that contains two members. The first member in dependent will be X, and then the second will be called Y. Okay, so I'm just going to make this slightly more compact. Now the one that you see, the code that you see in the sample code, of course is very straightforward. In order to combine these two, I'm going to replace the independent variable by a tuple which contains X and Y. And the first member in the dependent variable is Y, and then this will be X. Then I'm going to define my dy dx and dy dt. So my dy dt is this. So I define dy dx and dx dt in a single model, and I'm going to return two quantity instead of just one. Okay? So try to see the difference between this and this. Okay, so in this example, there's only one x goes in and one dy dx return. But in principle, the return can be output in the forms of an array. Okay, so you return it in a pair of quantity dy dx and dx dt. So you define the dx dt and dy dt to this. So the x is the first member in dependent variable, and y is the second member. So once you have defined this one, then we can define our initial condition. Initial conditions. So in this case, the initial condition has to be the initial condition for x and y. Okay, so the first initial condition should be initial condition for x, and y should be initial condition for y. So I'm going to enter here the values for x naught, and then the values for y naught. Okay, so what is x naught and what is y naught? So here x naught is 0, y naught is also 0. So both of this is 0. So this number would goes into the definition for the initial condition. Okay, so this will be then passed into the ODE integrate. Okay, so again model, and then initial condition, which is an array or tuple, and then you have a TARR, which is your linear space, np dot lin space. And so where should the number of first obviously should begin from 0. So you don't want it to be too large for the t. If the t is too large, then this is going to become exponential decaying. So you don't set t to be say 100. So if you set t to be larger than 1, then it will exponentially decay to 1 over e after 1. So maybe this should be between 0 and maybe 3 would be fine. If it's like 30, then you would not see anything after 3. Maybe 5 would be just fine, because it would be like 1 over e power 5. And then let's find 100 point and see whether it works. So what is the output? So the output is a solution which is in 2 columns. Now this is important. The output is in 2 columns. The first column here, well, I can't highlight this. So the first column is this number. Okay, it should refer to the values of the function x, and the second column is the output for this one, y. Right? So the variable, whether it's x or y, depend on how you define the initial condition. So if you define the initial condition for x first, then the output for the ODE INT, the first output would then be the variable that corresponds to the initial condition that you define in initial condition. So the second one would be y0. So be careful about this one. So we need to extract out the values from the first column. Right? So this is the first column. How do you extract the first column? So let us try to do this. So that is the SOL. So SOL is a 2-column vector. So now let's try to do this trick. Okay, so this is how many numbers? So there are 100 row and 2 vector. So if you want to extract the first column, you can't really extract it like that. You have to make a transpose. To transpose the array, so let me try to show you the shape. The shape, the NP shape of SO is this, right? So you have 100 row and 2 columns. Now, if you were to make a transpose to the SO, then what you get a matrix of 2 times 100. So the 2 times 100 matrix which is obtained from SO, like this one, would give you easy way to extract the first column and second column. So in order to extract the column, the first column from SO, you have to do some simple tricks. So let me print out this. So let me try to do something. Okay. Now solution 2 has been shown. Okay, maybe I'll just print the solution. So the solution looks like this. Now what happens if I transpose it? Then it will become a different matrix. So this is a matrix which is different. Okay. Okay, maybe I print it like this. So if you were to have only the solution, that is a 100 times 2 matrix. But if you transpose it, how do you transpose it? You transpose very easily. You say SO is equal to SO.T. Well, basically, SO.T is to make a transpose of the 100 times 2 matrix. So once you have transposed it, then you rename this as SOL as well. So in that case, when you print a shape, then it will be 2 times 100, right? So if it's 2 times 100, then the SOL, well, let us print out the SOL and see how it looks like. So this solution is then a matrix of 2 rows. The first row is the values of X, and then the second row is the matrix for Y. I can't highlight it here. So let me show you. So number 0, the 0 component is the first is the X value, and then if you type SOL2, then you get a second element in the matrix of SOL, which has been transposed from the output of ODE INT. So let me say it again. If you were to print out the solution from the ODE INT, you get a column vector. It's a 100 times 2 matrix. So what we want is the X component, which is in the first column, in the 0th column, and then the Y is in the first column. Now, in order to do that, you just have to type there, obtain the transpositions. When you transpose it, then the first column, or the 0th element in the transpose of SOL would be the X, and then the first element in the transpose would be the Y. So that's how you do it. So X solution is then defined to be the solution of T transpose number 0. Then X solution will be then T1. Right? But this is actually not a very elegant way. Well, not to say not elegant. So what you do is that first of all, you transpose the T. After you have transposed the T, then you rename it as SOL. Right? So this SOL and original SOL is slightly different. This is a transposed version, and this is not a transposed version. Okay. Then you call SOL to be SOL 0, SOL 1. So by doing that, you only carry out the transposition operation once here. when you want to define your x XOL and y XOL, you do not need to then to perform the transposition again. So the transposition is transposed once and is used by XO and YSO, right? But if you do not do like that, if you do like this, for example, then you don't need to have this. So in that case, your XO, in order to obtain it, you have to transpose it once, and you want YSO, you have to transpose it again. So you have to do 2 times transposition, which is redundant. So the good practice is that you just say SOL dot T, then you just don't make the transposition anymore. So that's how you do it. So now we are in the position to plot XO, TARR, XO. Okay, so that is our solutions, and then you label this, well, call it label equals to XO, and then I plot again, I plot TRR Y solution, then I say this is Y solutions, then I plot legend, okay, then it will show legends like this, then it will show 2 graphs in one shot. And you don't see 2 because they are all overlap each other. So in order to see both, maybe what you should do is that for one of these, you just have to make it to have a different form. So maybe you just dot the one, and then the other one you just make it as a line. So you see dot. Okay, maybe this is not defined here. You have to define right after this one. Okay, the label will come in later. Okay, so now you see there are actually 2. One is at the background, blue color one, and then the dot one. So both of these solutions are the same. So that's how you can put 2 differential equations into one single model. Instead of having defined 2 models for 2 different equations. So this works for if 2 differential equations dx/dt and dy/dt are independent from each other. However, if they are coupled, that is if x and y are 2 coupled functions, the same thing can also be done. Okay, so this is what we're going to do for this part, which is solving simultaneous equations by defining in the same model 3 coupled differential equations. So the trick is to define the coupled differential equation in a systematic manner, right? So this is what we're going to demonstrate to you. Now, any questions at the moment? Now, the reasons you come to this class is to ask me. Okay, fine. So you see, you can always look at me and I go to the YouTube, but why do you still want to log in at 3 o'clock in real life lecture like this? The reason you log into the real life lecture is because you can interact with me, right? So if you do not interact with me, then sitting in front of your laptop now or go to toilet, I wouldn't know, right? You can always watch this video online and YouTube, so that doesn't make much difference. But if you don't ask any questions or give me any feedback, then you really defeat the purpose of attending this live lecture. Okay. Anyway, so we are going to do this. So this is another example of 3 coupled differential equations where h, I, and t, h, I, and b are 3 functions that are coupled, right? So h depends on v as well. Well, h depends on v. I depend on h and also on v. V depend on also I, right? So basically, when I change, then h and the other 2 functions change as well. So in this case, the independent variable are h, I, and v. The independent variable are t, and there are many parameters: k1, k2, k3, k4, k5, k6, k7, k6. Okay, so you can pass the parameter by using the argument, like I do here, or you can also do the calculations by not using the argument, because the argument value for the parameter would also be automatically read in by the functions. So let us try to do this. So to make my life easy, let me copy this. I think I need this. Okay, that's all I need. Okay, so let me reproduce the solution for these equations in a new panel. Okay, so cut and paste. So let me clear the kernel. Okay, so this is the first three line is simple. It is just a 3 line. Then I define my model. Now to make my life easy, let me try not to do the argument thing. I think the argument could be sometimes quite confusing. Okay, so you can learn how to use this thing yourself. Okay, so I define my model. So the model read in independent variable and read in dependent variable. So this is my model. The model should contain the information for the differential equation. So what goes in are 3 independent variables, and what goes in also is the independent variable, which is t. Okay, so the independent variable is just the t. Okay, nothing but just a t. I define a dependent variable that should contain 3 members. First member would be the variable h, second member would be I, third member would be v. So this is the dependent variable which we are going to define in the initial condition later. Okay. So now I have to define my dh dt. So obviously dh dt is just a parameter k1, k2 times h minus k3, h and v. So this is how I define my dh dt. So dh dt is just a name. Okay, dh is not really derivative, it's just a name so that I know that this refers to the h dot. So it is equal to k1, k2, k3. H is defined in the first line, and hv is also defined. And then vi dt is just this one. It's just a k3hv minus k4i. So that is how I define it. And so it's so I have to define the values, okay, because all these k are numbers. So the k are the numbers which I have to define in the beginning. So I define my k here. So usually the parameter, which is a constant, should be defined in the beginning. Then I define my t linear space in the beginning as well. And then okay, this is the initial condition. So the initial condition are fixed by 3 numbers. So the first number is given to be h0 and I0 and V0. Now this is actually a model for HIV virus. If you read the original text where I quote from, I think I quote this from one of the from this app monitor code. So it is a modeling to predict the numbers of HIV cell. So I think H is referring to something, I is referring to something, V is something. So I think, if I'm not mistaken, the V refers to the number of maybe some cell that is in the sample of a HIV tissue or something like that. So I think initially, so I think V is the virus. I think initially there's 100 virus in a cell, and then maybe there's a median of healthy cell, and then I is the, I think it's a drugs or some treatment. So initially, I forgot, I think I is something, but anyway, this is a model of a real life biological system. But it tells you initially, the healthy tissue is 1 million, and then there's a virus in 100, and then this refers to some kind of interference from medicine or something like that. Then you would like to predict how many numbers of cells still survive after some time later, and then what is the numbers of virus that will occur in the sample after some times later. Okay, so the behaviors of the numbers of cells and the virus at some time later is governed by this set of coupled differential equation, where these parameters are obtained from experiments. So they do experiment, then they count the numbers of virus and the cell at different time, 1 hour, 2 hours, 100 hours, 200 hours, then they collect all these numbers, then they fit the behaviors by using some kind of modeling, and then they work out that these are the parameters that best fit the experimental behavior. But from our point of view, we just solve this as a coupled differential equation, where we just take this number as constant given to us, and then we just want to use the ODE solver to solve this coupled differential equation. Okay, so you have to define the initial conditions, which is this number. So this initial condition, it would be what I define here, initial condition. So the first initial condition is HI, and then it's V. So when you call the ODE solver, this number that would go into the model. So when it goes into this model, the H0 will be assigned to the first variable. I0 will be a number that would assign to the variable 1, and then V0 will be assigned to the variable V. Right. So I'm just saying that the sequence of defining your initial conditions is very important. Okay, so it depends on how you define what is your H, what is your V, and what is your so in our model we stick to the norm that H is the first variable, I is the second variable, V is the third variable. So if you mix up the sequence of HIV, so when you supply the initial condition in a wrong or inconsistency sequence, say for example, instead of supplying the values of H0, I0, V0, you supply say V0, H0, I0. Then this number goes into the solver, will give you a wrong answer. So once you do that, then ODE, DE, EINT, then of course you call the model to supply the initial condition. I think that is it. Then TARR. So when you press the button, you will see 3 output. Let's see 3 output. Yeah, 3 output. So you see 3 columns. So the first column value is a number for H. So you see the first number is 1 million. So this 1 million should refer to H0, which is defined as 1 million. And then the first value for V0 should be 100. So this is 100. The number is 100. And then this is 100. So this refers to the V0. And I0 is the numbers of whatever thing that is not present in the beginning. So it's 0. So then let us extract the solution for H. So H is the solution. Well, let me call this SOL. Then H is the solution. You transpose it. Well, maybe the solution again is equals to solution transpose. Then the first component in transpose will be your H, and then I is the second component, HIV, and then the third component will be HIV1. Okay. So not yet. Yeah. Well, of course, I think it's almost done. Then let us plot PLT dot plot. See whether it works. So TARR H. So this will plot me THRR versus. So this is the values of H. But according to the questions here, we want to be slightly more complicated, because these are revolving numbers of cell, right? So when time passes by, the numbers of virus will explode. The numbers of cell will also explode, because this is a real life biological system. So 1 become 2, the 1 cell will split into 2, 2 cell will be split into 4, 4 will split into 16, and things like that. So the numbers that involved in H, V, and T are actually expanding exponentially. So if you look at the solution, it's like decreasing from don't know how many zeros up to how many zeros. So the variations in the function's value as a function of time, even though it's from 0 to 10, would change a lot. So for real life system like that, where the values of a function crosses many orders of magnitude, it would be best if you were to plot the function in terms of log scale. So we're going to plot the y-axis in terms of log scale instead of plotting it in linear scale. So this is in the linear scale. So we plot this in the log scale instead of just plot this. So what you do is that instead of plot this, we said, I think semi-log y. I think that is what you mean by that. You plot semi-log y. Then that means y, semi-log y would mean that the y-axis will be in semi-log, so in the log scale. So let's see it works. Not yet it works. So it says that this scale is a log scale, right? So that you can see the variations much more clearer. So if you plot it with just a log scale, then it would not be. So you see the scale here is a log scale. So the scale, like this is large, this is large, this is small. Now I just want to remind you what is a log scale. I don't talk it in detail here. When you do in your first year lab, especially when you deal with, say, I think radioactivity, sometimes you plot your graph on a log scale graph. So in the olden days, we have this graph paper. You have normal graph paper, you have semi-log graph paper, you can have double log graph paper, right? Where x-axis is also a log graph. So let us plot this. Then we also plot not only this one. Let us plot also, I think label equals to h. Okay. So after we have done that, let us also plot this to be say not red color. Oh, this red color dot. No, it's wrong. Label maybe this one. It's also wrong. So I think I must have done something stupid. Label. Okay, this label. I think this label. Okay, so it's a label dot, which is a red color. So it's red color dot. Looks like this. So this is done for the h versus r. Let us plot another function. Hiv, hi, and then this is changes to, I think, like blue dot. I don't know what is this, whether BO works or not, but let's try HI. So BO doesn't work, so there's nothing called BO. I think maybe W, yellow, Y dot, it doesn't work, but it doesn't matter. If it doesn't work, then I just don't label it. I just label it, but I just don't call the follow keyword argument. Let me just leave it like that. Okay. So TARRI, and then now I'll just throw this away. I'll label it later. And then TARRHIV. So you have three graphs plotted together. Okay. So let us see if I can label this properly. Semi-log. Maybe let's try this work. Label. Does it work like that? I'm not sure. So anyway, H I V. Does it work like that? I'm not sure. H I V. Maybe it doesn't work like that. Label. No, it doesn't work like that. Label. RABEL. H I V. No. So try it again. So maybe just label the H. So if I label the H, would it work? Just label the H. No, it doesn't work. HIV. No, I don't know how to label this, but just leave it like that. You have three graphs plotted together. 1, 2, and 3. So that's how you solve the couple differential equation. So the labeling, the graph, the plot of x and y are what we call cosmetic. Okay, so we take a break at the moment. Then we come back at 4:10. So at 4:10 we continue to the next topic. Okay. So any questions, you can stay back and ask me. So I let you to scan the attendance at 4:10. I'll be waiting for you to take a break. Any questions, just ask me. Okay, so let's come back. Okay, let me attend some of your questions. Some of you is asking, saying that assignment 8.1 question 1, assignment 1 question 1, assignment 8.1 question 1, when for plot it should be dy dx equals to t. Let me check the questions. Dx dt equals to this, dy dt equals to 1 over x. So it's a couple differential equations. Dy dt equals to x. So that should be x. Okay, let me check. So that should be 1 over x. So what I get? Okay, let me try again. Now let me find out my solutions. And I appreciate that people tell me some questions. Okay, I'm checking the solution for the assignment 8.1. 8.1. So I have a solution 8.1. Yeah. Now do I set it as 1 over x or set it as 1 over x or x? Okay, so the answer is here. X over mu. Okay, so it should be. Okay, so maybe I check this. Okay, so maybe I was wrong. So it could be dy dx equals dy dt equals to x, not 1 over x. Okay, so maybe I change it here. If it's wrong, then I'll change it again. Okay, I keep on correcting this. So this is assignment 8.1. So I change it to x. Okay, maybe you are right. I normally don't have confidence on myself when it comes to this kind of thing. So I change it here and I save it. So it has been saved. So when you check it again in the link, it should be updated instantaneously. So I'll go through this again in case it has some problem. Then we'll come to solve this later on. Okay, doesn't really matter. Okay, fine. So now you could solve this quite easily. Yeah, I think it's just problem x0 equals to 1, x at 0 equals to 1. Yeah, I think maybe you are right. If you see if dy dt equals to 1 over x, that will mean that dy dt will be infinity in the beginning. But never mind, I'll check this maybe later. But you try your best first. But this should be the correct solution. Okay. Okay, so let us come back to the next part. We have finished the part. We have finished the part 7. Now we are going to do part 9. Now the part 9 would be slightly more complicated. So the part 9 is the second order differential equations. Which is like this. We are going to solve a second order differential equations using the ODE solver. But in these situations, things will be slightly more complicated. It will take a few more lectures to cover this one. Now, once we enter the solutions of second order differential equations, we are going to go into something more challenging. The reason is because second order differential equations is very, very common in physics. It's much more common than first order differential equation. As I explained in last lecture, Newton's law is second order differential equation. So if you use Newton's law to write down the equations of motion to describe the dynamical systems, you have a set of differential equations which is in second order. So in order to understand the dynamics of this sort of complicated system, for example, systems of many springs stick together. So these systems would interact with each other. Say maybe we would have 10 different balls. Each ball would stick to another ball through a string or spring. Then all these balls are moving according. To the law of physics written down by the Newton's law. So this would end up with a set of many couple second order differential equations. So let us look at a few common differential equations as the second order that you have seen in most of your syllabus. Now, one that we've seen earlier on is in drag force, right? That when object fall down, right? So when object fall down, it suffered a gravitational pull mg. At the same time, it has this density, not density, you have this drag force moving in opposite direction. So when object is falling downwards, the drag force will be moving upwards. So we ignore the buoyant force. We just look at this, the density force, which is mu minus b. So the b here is the k that appears here. Okay. So this is the equations which is written down using Newton's law. Left hand side is the acceleration. Right hand side is the net force. Okay. So net force comprised of the gravity that is pointing in the opposite direction to dy dt. Dy dt is the velocity. So the g has a sign which is positive and opposite to the sign of dy dt. So it means that the gravitational force is moving in the opposite direction with respect to the velocity. So that is the net force, and then the net force will cause the object to accelerate along the y direction. This is d to y dt squared. So a second order differentiation, you want to know how y change as a function of time. So to solve this, you just have to solve the second order differential equation. We have seen this in a few lectures earlier on, right? One more or less. That is a very common thing that you have seen also in your ZCE 103 when you talk about wave. Wave is basically very similar to a simple harmonic pendulum. So a simple harmonic pendulum like this one, when you derive the Newton law for this, then you derive all this. So I think in your Form 6 of articulation, you learn all this stuff. So when you displace a pendulum from its equivalent position, a restoration force will tend to put it back towards the central equivalent position, and it turns out that the restoration force, which is this one, is always inversely proportional to the displacement. So in situation where the restoration force is proportional to the displacement but opposite in direction, will always result in a simple harmonic motion. So this is a very, very important concept in physics. So if you do not know about this one, then you are not learning physics properly. Okay. So a pendulum like that, a spring which is displayed from its equivalent position, also displays similar behavior. That is, the restoration force of the spring would always be proportional but opposite direction to the displacement. And then you also have this situation of, say, a block of ice that is floating on the surface of water. So the equivalent position is the position where the block of ice that's floating. So if you press the block of ice a little bit, depress it by a little bit, let go, then the ice will also execute simple harmonic motion. So in that case, the restoration force comes from the buoyant force and gravitational force as well. So that force will always tend to restore the position of the block of ice back to its inverse towards its equivalent positions. So all these are very common law that you see that is described by the situation where the second order displacement. So here the theta refers to the coordinate, displacement coordinate, and the second order derivative of the displacement coordinate with respect to time is always inversely proportional to the displacement time in constant, and this constant will determine the frequency. Okay, so if the medium has a very strong restoration force, then the frequency will be very high. So in this case, for example, the restoration force comes from the gravity, which is g. So if g is very large, that will cause the frequency omega to become very large as well, right? So if the g is very small, then the frequency is very small. So if, for example, if the restoration force comes from the spring, so if the spring constant k is very large, then you expect the frequency with omega will be very, very large as well. So the stronger is the restoration force, then the faster, the larger is the frequency of oscillations. Okay? So this is another example of second order differential equations, simple harmonic motion that you see in physics. And what else? Okay, you also have this one. You have seen this in your ZCE 103. ZCE 103, yeah, ZCE 103, your wave and optics. So in this case, you add in a drag force to the pendulum. So instead of just the pendulum moving under the shear motions of gravity, you could also have a drag force. and you may also subject the pendulum or the simple harmonic oscillator under an externally applied force, which has a different magnitude and can be exerted into the pendulum at different frequencies. So this is a force system with a drag force other than just the gravitational force. Right? So this is a damped pendulum with external driving force. It accepts the influence from the gravity and from the medium where it is oscillating, and also you may also control experimentally some external force to act on it at a given frequency. Okay, so if you add in different things, then the behaviors of the pendulum would behave differently. So the gravity is almost constant, but the effects of the gravity could also depend on the length of the pendulum, right? So if you use a shorter length, then the pendulum will move faster as well. This is from the medium. The K is a medium. So how strong is the drag force or the damping effects on the pendulum depend on this constant K, right? So now sometimes we just lump the constant K into this parameter called C. I think C has a name called the damping ratio. So damping ratio is a result of the interaction between the pendulum and the medium it is in. Right? So if, for example, you put a medium in a vacuum, C will be 0. If you put a oscillator in, say, water, then the C would be non-zero. That will cause damping to the oscillation. So you must understand all these interpretation of each terms in the equation of motion for a dynamic system. This is how you learn physics. You don't memorize the formula, but you try to also understand the interpretations of each term. Right? So this term from the gravity, and this term from the medium, and this term from the external force. And this is a force that you can control. This is the frequency of the force you can control. And you put in different medium, then the C would differently. And this omega is describing the restoration frequency, right? So it is constant. It is primarily depend on the natural frequency of the gravity, right, or the pendulum under the pure effects of gravity. So frequency is an constant defined by this ratio, and then this is also constant, and this is also constant. So if you were to apply different values of K, different values of omega, different values of Ft, then the solutions of this theta would move differently. So theta is the values of angle that change with respect to time. So you can have this situation, right? For example, if you switch off the external force, and if you switch off also the damping force, what you have is only the pure oscillation. The pure oscillation would then be just this one. You just have a simple harmonic motion. But if you switch on a damping force, say you switch on this damping force, it will become non-zero, and you switch off the frequency at all, like this F force is just 0, then you could have this damp situation where it oscillates and then it would dies off. If you switch on the C to become larger and make C to be exactly equals to 1, then you will have this critically damped situations. And when the C is much larger, then you have this overdamp. Okay? So usually the real situation is that the C would be between 1 and 0, then it would be underdamped. Most of it are the underdamped situation. This is underdamped. If it's critical damped, the characteristics is that when you arrive at critical damped situation, the pendulum will not even complete one oscillation, right? So if it's underdamped, then even though the oscillation is damping, but it will still complete a few cycles of oscillation. But if it's critically damped, that means it would not even complete one oscillation. So these are the damped oscillation that you learn in your 103 physics. Now, if you switch on the force, then things become complicated, right? So if you switch on your force and you switch on your frequency of this applied force, and if you apply force omega d is set to be equal to the natural frequency, and you set depending what you call the damping ratio to be 0, then you have a resonance that goes to infinity. But this is not happening in reality, because in reality you always has an damping, right? So it's not possible to have an oscillator where there's no damping. It's always have a damping. So in situation where the omega is close to the natural frequency and damping is not 0, then and the force is not 0 as well, external force is not 0, then you have a situation where the resonance will not go to infinity, but the peak of resonance will be somehow right at some maximum, and then you have a finite situations. So this is the reality lah. Force not 0, omega very close to natural frequency. This damping term will sort of attain the infinity from the resonance. Okay? So you can actually see the behaviors of this C as a point of time by solving this differential equation. Right? So you set in different values of the damping ratio, different values of omega. You'll be able to obtain how omega, how this theta change with time. So I think this is one of the exercise we're going to see. So first of all, we will solve the second order differential equation for a pure pendulum without any drag force, without any damping, without any external force. And then you define blah blah blah, then that's how you could do it. So we solve it. So before you solve it, you should already know what's the solution. The solution for a harmonic oscillator looks like theta equals to sine omega t with two more additional constants, which is the amplitude as well as the phase. So these are the numerical, these are mathematical solutions which should be known to most of you. So maybe I should type it here. The solution for these equations is this. Okay, maybe I just type it here. The analytical solution. Maybe I just type into the original text would be better. Part 9. Okay, this is one. Okay, so the analytical solutions could be this one. Omega equals to this one. The analytical solution is this. It looks like it's a theta. Theta as a function of t should then be theta naught. Okay, I think it's theta 0, which is the amplitude that you set in the beginning, which is in constant times sine, and then omega slash omega t plus and phi. And phi is a constant. Okay. This theta naught and phi are constant fixed by the initial condition. Okay, so you fix your initial conditions in terms of saying theta at the beginning 0. So what is the values of theta, and then also theta dot thing, theta dot which is the values of theta and also values of d theta dt at 0. So this one. Okay, so this is the new line I type in, so I save it. So the analytical solution for these differential equations is this one. So you plug this expression theta naught plus sine omega t plus phi into these equations, you get the solutions. Okay, so you learn how to solve this differential equation second order in one of your differential equation courses, maybe last semester or maybe next semester by Dr. Linda. Right, so you assume some form, then you just plug in. I think yes, the second order differential equation is part of your syllabus. Most of you should have gone through this. Dr. Linda was teaching that. So in this case, the values of phi and this theta naught is fixed by the initial condition you fit in. Right? So this is how fast you set the motion of the harmonic oscillator in the beginning at t. For example, if you displace the harmonic oscillator in the beginning by say 5 degrees, then you let go. So when you let go from rest. So in that example, your theta naught is then 5 degrees, and then your theta naught, which is the rate of change of the angle at the time t goes to 0, is just 0, right? So it's just the angular speed of the pendulum when you let it go. So once you set in this one, then you get solution. Okay? So in that case of phi will be I think 90 degrees or something like that. So anyway, these are just an theoretical solutions. That is what you expect. Right? So when you obtain the solution of theta, then you plot it out. Now since theta is an sinusoidal function, d theta dt should also be another sinusoidal function. For example, if theta is sine, then d theta dt should also be cos. Okay, so it will be cos. Differentiate of sine give you a cos. Now I want to explain this term theta dot. Right? Dot means d theta dt. Right? So d theta dt and d dot are usually the same. Right? So most of the time we use a shortcut. Theta dot would means d theta dt. So we're going to define this theta dot as d theta dt. Right? So now to solve the second order differential equations in Python, you have to break the second order differential equation into the form of first order and second order. Okay, so I think the trick is that if you are given second order differential equation, you have to break it down into two first order differential equations. So you define theta dot as a new parameter, and then you differentiate the theta dot and then express this d dt of theta dot in your model functions. So in your model functions, to solve a second order differential equation, you have to return two output. The first output is the output for theta dot, and then the second output is d2 theta d squared, which is called d dot dot. Okay, so let me say it again. To solve a second order differential equations, you have to define your model such that the model will return two output. First output is theta dot, and then the second output is theta dot dot. So ODE, the differential equation solver, ODE INT, would then take in theta dot and theta dot dot to return you the solution you want, which is theta and theta dot as a function of time. Okay, I couldn't write it. Maybe let me see if I can write what I meant here. Okay, so let me call out this whiteboard. Okay, I'll try to write on this whiteboard thing. Okay. So what I'm saying is that you have a model. In this, your model MODEL. So what you do is that in your model, say just call X. So this X would be made of theta and theta dot, if I'm not mistaken. Theta dot, no, sorry. But this is what I meant. Now what I meant is that in your model of X, So finally, you will return to output. Return TURN. So what you return is that you return theta dot, and then you return theta dot dot. Okay. Then when you call your ODEINT, well, this is ODEINT anyway. Then this ODEINT, what you do is it would read in the model, MODEL, model. Okay, so the ODEINT will read in the model, where the model is this one. Then after the model process the initial input, it will return theta dot and theta dot dot. So what this ODEINT do is that it will convert the theta dot into theta. So this theta would be coming from the theta dot. Then this theta dot dot, when it's processed by the ODEINT, it will give you theta dot. So in the whole process, you define your model to return theta dot and theta dot dot. Then ODEINT would return you the expression of theta and theta dot. So there will be two outputs coming from ODEINT. It will give you not only theta but also theta dot. That is what I try to tell you. I'm sorry that this pen mouse is difficult to write. Any questions from the students? Hopefully that you are still there. We still have another 20 more minutes to go. Okay, so let me show you roughly the structure. So here the output is this. So this is the model, right? So the model will return to output theta dot and theta dot dot, and as a result of the ODE solution, it will return to output as well, the first output and the second output. So the first output from the ODE model would be the values of theta, and the second output would be the output of theta dot. So when you finish doing that, theta dot is the solution we are looking for, is given from the ODEINT, and theta dot dot will also be returned. So when you plot the theta dot and also theta, right? So here is the solution. So this is the solution, which is the sine function, and this is the theta dot dot solution. So one shot you have two output. Okay, so this is how you do the second order differential equation. I give you a second order differential equation, you would be able to obtain the solution of theta as a function of time, and also theta dot, which is d theta dt. So you have two output. Now this is to be different from the previous example, right? In the previous example, when we solve the first order differential equations, you have only one output, right? In your first order differential equations, which is the y, right, or the h, or ai, or v. But you do not need to have a dh dt, or di dt, or dv dt. But in the second order differential equation, not only you have a solution of x, but also x dot. Okay, so this is what we're going to see. So once you know how to solve the second order differential equation for a simple pendulum, then it should be straightforward, or almost straightforward, to solve a more complicated second order differential equation. So the damped pendulum and the simple harmonic pendulum are almost identical except for this term, right? So we add in the damping term to the Newton's equation. So when this is added in, this represents the damping force. So when you add in damping force, then you have additional dependence of the angle theta on time, then the solution will be modified. So let's see how you do these solutions. If you know how to do this, adding in additional term on the right hand side will become like this, And then how do you solve it? So you will solve the theta dot and then the theta dot dt. So you have to generate this expression in your model. Then we will see the details in a minute. I just want to get you some overall idea of what you expect to see. So this is the solution. Okay? The solution of a damped pendulum, which makes sense to you, right? So if you switch off the pendulum to have no damping, where the C is 0 or very close to 0, then you have many oscillation which is not damped. But once the C is not 0, say 0.01, 0.02, then you start to see damping. Right? So you see the behaviors of the solution in front of you if you write a numerical code to solve it. So this is something that you will not experience when you learn your ZCE 103 if you just solve it analytically. Right? So if you solve it numerically, you can tune the values of C, which we will do later. Every time you put in a different C, then you see different damping behaviors. Okay? So you can overlap many behaviors with different C, then you can see now for C larger, then the damping is more serious. C is smaller, then the damping will be less. Okay, so this is a numerical behavior that you could easily simulate using Python. Okay, so then the other example would be the projectile motion. Of course, everyone would learn this projectile motion, 2D projectile motion. You throw an object in this two-dimensional space. You have x direction, you have y direction motion, then the x will just keep on moving at a constant speed. The y direction will be falling under gravity. So when you throw a ball at some angle, at some initial speed, when you solve it, then you have a two-dimensional motion. But if you just look at the one-dimensional motions, then this is the equation of motion that control the y motion along the g direction with a drag force. So this is an equation of 1D for velocity of object moving in the vertical direction, experiencing a drag force. So you can couple this to a two-dimensional motion, right? So the two-dimensional motion will be described by a set of equations for y and a set of equations for x. So in this case, to make life easier, we do not have any drag force effects on the vertical directions as well as on the horizontal direction. But here you have a couple, well, not couple, this is a non-coupled differential equations for x and y. So in this case, x and y are kind of independent. But you can solve these second-order differential equations in a single ODE functions, then finally you get this. Okay? So you can solve these equations and then you can write the code, then you get this. Okay? So I think this is what we're going to see. Then you can also simulate the result of this. So this is just static simulation where you just plot the function of y when they change with t, x when they change with t, then you combine the coordinate of x and y, overlap them, then you have these solutions. This is the y coordinate, this is the y coordinate along the x-axis, the y-axis, and this is the x-axis. So you can combine them together. So all these points will be generated by solving the differential equations for the motions numerically. Right? So let me say it again before we go into the really difficult hardcore stuff. In physics, the dynamics of systems are governed by a set of equations of motions. So these equations of motion are basically Newton's law, Newton's second law. So using Newton's second law, you apply it, then you write down the forces, net forces on the system, then you will be able to derive the net force. Now once you derive the net force, then you can solve for the coordinates as a function of time. So that is a set of second-order differential equations. Solving the second-order differential equation will allow you to predict how these coordinates change with respect to time and how the velocity of this coordinate change with respect to time. And your job is to solve it numerically using the ODE solver. Now once you have solved this theta dot numerically, then you can visualize how this theta change with time. Right? So this is all well-known equations. So I picked this as an example from your first semester, from your first year, from the secondary schools, equations that you have seen before. So you can simulate them in this Python class. Later on in chapter 9, chapter 10, we will learn some dynamic simulation where you see pendulum moving. Instead of showing the graph, which is static, we're going to see a simulation where you can show or display how this pendulum moves. For example, you have two-dimensional collisions and they collide according to the conservational law of momentum and also Newton's law. Then you can actually simulate how these objects bang towards each other and then disperse from each other and conserve the momentum. So these all can be simulated as long as you know the law of physics that govern them. Now, in more general situations, you could have equations of motion which you've never seen before. For example, in chaos. So in physics, you could have chaotic motions, like you could have these motions, which is a coupled equations of how many x and y degrees of freedom that is governed by a set of laws that bind them together, interacting. When you solve this, you will never know how they behave, and then you can do this numerically. So once you can capture the equation of motion for this dynamical system, then you translate them into code, then you solve it, then you visualize it. Then you find out that the solution is displaying some kind of chaotic motion with fractal geometry in it. So all these can be studied only if you know how to translate the physics into mathematics and then translate again the mathematics equations of motions into a Python code. Then you visualize them. So it's very powerful code. You don't do experiments. As long as you know the law of physics, then you'll be able to predict all these motions. So this is not only exercise for you to pass an A and graduate and find a job. What you learn here is a very useful trick, right, to translate equation of motion into visualization, and at the same time learn and appreciate what physics can do for you. It's a set of equations that governs how nature would evolve in time. Right? So if these equations are very complicated, then no one knows what will happen to the future. So you can predict them. For example, people predicted that the planetary motions in the long run will become chaotic, in billions and billions of years later. So if you allow these planetary motions of solar and all these 8 planets around the sun, and if they allow them to evolve long enough, although you know the equation of motions, you solve it, then you predict that finally after many billion years, then the motions of this planet, instead of becoming just orbits, ellipse, it becomes chaotic. We cannot predict the behaviors of it. So these are called chaotic physics, which is closely related to programming. Okay, so if I were to continue talking about the solution for this, then you would be bored to death. Okay, so anyway, before I let you go, I just want to check on the assignment that I prepared for you. So I think I have done an assignment. So the assignment that I have submitted earlier on, I think is assignment 8.1. Okay, so assignment 8.1 is an assignment that is like this. Okay, so maybe now you can't do this, right? So you're supposed to solve a second order differential equation for this, but since I do not have time to show you a complete solution for this, maybe solving a first order differential coupled differential equation would be fine. Maybe I will modify the assignment 8.1 slightly. So maybe I add in one more coupled differential equations of first order, so that you can solve it. Maybe there's some problem with this one, but that doesn't matter. So there will be only 2 assignments for you, which is very easy. But I want to make sure that you have some exercise to do 2 questions. So maybe not now. I'm going to take this question 2 away and replace it with a new couple first order differential equations. Okay. So maybe wait until tonight, only then you start to attempt on assignment 8.1. Okay, so that's all for today. Any questions? I'll be happy to answer your questions. So it is 4:53 at the moment. We still have a few more minutes to go. I think it's very tiring, right, to listen to 2 hours of lecture. But take this opportunity to ask some questions if you want to. Okay? No, like usual, no people want to ask anything, then I'll stop our lecture here, maybe within a few minutes after I have done with this, I'll upload the YouTube, and I also will modify the assignment question 8.1 so you can do. Okay, so that's all for today. Any question or any feedback, I'll be happy to listen from you. Okay, that's all for today. Okay, bye.